Alright, we're going to go through the steps on how to design a beam or pick a beam for our design here. And so you can see that our grid is spaced at 10 feet for the beams. And so we're going to be designing a beam. We're going to say for right here, and I'm going to call this beam A. Alright, a couple of things that we need to know. The dead load requirement for our structure is 80 pounds per foot squared. The live load is 120 pounds per square feet. And the yield stress of structural steel is 50,000 pounds per square inch. All right, so the first thing that we have to do is we have to figure out what the uniform load is, the uniform distributed load for the dead load. And so the uniform distributed load for the dead load is equal to the dead load, which is 80 pounds per square foot, times the tributary width of our beam. The tributary width of our beam, remember, is halfway to the next beam on either side. And so this beam is supporting all of this area above it. And so in this case, because there are 5 feet between beams, our tributary width for this beam is going to be 5 feet. And so we'll multiply that by 5 feet. So you do that and you get 80 times 5 will give us a uniform distributed dead load of 400 pounds per foot. The next thing we have to do is figure out the uniform distributed live load. Which is equal to our live load, which is 120 pounds per square foot, times our tributary width, which was 5 feet, which gives us a live load of 600 pounds per foot. And so now to figure out the overall uniform distributed load, it's equal to our dead load plus our live load. So our dead load was 400 pounds per foot plus our live load at 600 pounds per foot, which gives us a uniform distributed load for this beam right here, beam A, of 1,000 pounds per foot. The next thing we're going to do is calculate the reactions on our beam. And so we remember from our formula sheet that we have here a uniform distributed load. The reaction force of A is equal to the reaction force of B, which is equal to the uniform distributed load times the length of the beam divided by 2. And so we'll use that formula to figure out the reaction. So the reaction at A is equal to the reaction at B, which is equal to the uniform distributed load times the length of the beam divided by 2. So our uniform distributed load was 1,000 pounds per foot. The length of our beam is 10 feet long. We divide all of that by 2, and we get a answer of 5,000 pounds. So on our beam, on either side of it, side A and side B, we are getting a reaction force of 5,000 pounds. Next thing we'll calculate is the maximum moment. And so the moment max is equal to, we'll look at our formula sheet again. Here's the moment max for our beam. It's equal to the uniform distributed load times the length squared divided by 8. And so we'll go ahead and write that. The uniform distributed load times the length squared divided by 8. Substitute. We have 1,000 pounds per foot times our 10 feet squared. Do it like that. And we'll divide that number by 8, which gives us a maximum moment of 12,500 foot-pounds. Okay, the next thing we're going to calculate is the nominal moment. And so we haven't talked about nominal moment yet, and so I'm going to go ahead and write what we're doing here. I'm going to write nominal moment, and then we'll look at a formula that explains what the nominal moment is. All right, and so our formula up here, if we look under structural design, it shows us that the internal bending moment is less than or equal to the nominal moment strength divided by the safety factor. And so what a safety factor is it's built-in extra insurance basically on the beam that it's not going to fail. And so someone has figured out that for structural design, we need to multiply our numbers by 1.67 for it to be an acceptable safety factor for use in the structural design. And so our nominal moment, we'll go ahead and write that formula down. The internal bending moment is less than or equal to the nominal moment divided by the safety factor. All right, and so we'll manipulate that formula to get nominal moment by itself. And so to do that, we'll multiply safety factor by both sides, and we get that the nominal moment is greater than or equal to the internal bending moment times safety factor. All right, so then we'll insert our numbers. Our internal bending moment, we calculated up here. It's 12,500 foot-pounds. We'll multiply that by our safety factor, which is 1.67. And we will get that our nominal moment that we're going to use for the calculation is 20,875 foot-pounds. And so what this nominal moment does is it gives us, again, extra insurance. And so what it's saying is that this is the maximum moment that will be felt on the beam, but we're designing it to be able to withstand this moment. And so we have some extra safety built into our design. The next thing that we're going to calculate that we haven't calculated yet is called the plastic section modulus. So I'm going to go ahead and write that. And so what this number is going to do, this is going to be able give us a number that we're able to go out and find the beam that we want to use for our design based around this number. And so if we look at our formulas again here, we have plastic section modulus is right here, z of x, and so that times our yield stress is equal to the nominal moment. And so we can use those formulas and manipulate those to solve for our plastic section modulus, which is what we want to use because that's what we're going to use to determine the beam that we want. All right, and so I'll go ahead and write our formula down. The nominal moment is equal to the plastic section, or excuse me, the yield stress times the plastic section modulus. All right. We will use this formula. We'll place it up here in this formula because then we can substitute Mn up here for that formula, and so we'll do that. So we will say that the yield stress times the plastic section modulus is greater than or equal to our nominal moment We'll plug in our numbers now, and so we get solve for plastic section modulus substitute. Nominal moment was 20,875 foot-pounds. Our yield stress of the material we're using is 50,000 pounds per inch squared. And so one thing we're going to have to do is we're going to have to convert this number here to inches. And so we'll go ahead and multiply this by 12 inches is equal to 1 foot to get that number into inch pounds. So the plastic section modulus we'll look for, we'll go ahead and calculate this out. 20,875 times 12 to get it in inches divided by 50,000 gives us a plastic section modulus of 5.01 inches cubed. So we will then use this number to go out and determine what beam we're going to use in our design.